Welcome everybody to the Homi Bhabha Memorial Lecture, the sixth one in its series. The Homi Bhabha Memorial Lectures are an important annual event of the Department of Physics, IISA Pune, initiated by my predecessor, Professor Sunil Mukhi in 2014. And the whole idea has been to get very distinguished scientists in the field who come and give a lecture which is accessible to the broader audience and particularly our students on an area which is frontier. And we have such a speaker today. I'm happy to welcome Professor Yashwant Gupta to deliver the sixth Homi Bhabha Memorial Lecture. Before I introduce Yashwant, I wanted to actually spend some time giving you a few slides. As you see, largely courtesy of Professor Sunil Mukhi, who does a much better job than what I would be able to do of introducing to the next generation who Homi Bhabha was. I mean, I'm sure everyone has heard about Homi Bhabha, and you are actually situated on the Homi Bhabha road. But so Homi Bhabha is one of the most leading and legendary figures in the Indian science, and these are some of the pictures of his family, his place where he studied in UK, and his picture in the youth. So he was born in 1909 in Bombay and went to Cambridge to do a degree in mechanical engineering, and his family was hopeful that he would come back and join Tata Steel as a metallurgist. And as he had told his father, I have no desire to be a successful man, but I have a desire to do physics. And then he studied under Dirac, and there was a landmark paper on electron-positron scattering which still goes by his name. And this is a slide showing you that paper, which he wrote as a student in Cambridge, and this was communicated by his supervisor Fowler. He returned to India in 1939, and probably not with the intention of staying on, but the war prevented him from going back, and he joined ISC and set up a cosmic research unit there. And he was elected Fellow of the Royal Society, which shows you his stature in the field. And it's also said that C.V. Raman, impressed by his artistic abilities, which was an additional great quality Homi Bhabha had, and anyone who has visited TIFR would witness the amazing collection of art Homi Bhabha put together in that. It's almost like a art gallery if you walk through their corridors. So he described him as the Leonardo da Vinci of India. And then this is some picture from his cosmic ray days. And then the big thing that happened was to set up the Tata Institute for Fundamental Research. And he basically got the Tatas and the government of Bombay to get together and set up something which would do fundamental research and also start the atomic energy program. So his advocacy led to the Atomic Energy Act. And so essentially Homi Bhabha brought together three people: Nehru, who was quite visionary as a leader and supported science and technology growth in the country; GRT Tata, who's very well known for the kind of legacy he's left from the industry in our scientific institutions. And this is kind of little signature where of Jawaharlal Nehru talking about the Tata Institute for Fundamental Research way back in '54. And this is a quote which sort of defines what his thinking was, and it was mostly directed towards promoting the fact that technology is extremely important for the progress of a country. Access to technology and the ability to use technology and develop technology. But he was also very careful to always add that technology is derived from your efforts in basic sciences. And this quote and this one where he, sort of contributed to the drafting of of India's scientific policy resolution. Okay, so he says that you know the prosperity of the country depends on technology, raw materials, and capital. And the first is perhaps the most important. But what you should realize is technology can only grow out of an application, grow out of a study of science and its applications. So the fact that we are Institute of Science, and there are institutes of technology, but there's no, in my mind personally, I don't see a dividing line. In fact, science and technology go hand in hand, and which is what you'd hear probably in the talk that Yashwant provides. Uh, Homi Bhabha died very prematurely in 1966 in an air crash in Geneva. This is a picture of the memorial at TIFR Colonnade at that time. And he also brought Indian science, in touch with the leading figures of the international community. Okay, and his Niels Bohr, and then, various leading luminaries that you are aware of. Here's him with his partner who kind of really promoted him, the political, what would I say, the person who promoted this whole idea of Homi Bhabha's efforts to set up science and technology, patronage, from political patronage. And of course, here's a picture probably from Princeton with leading people like Einstein, Yokawa, Oppenheimer, and Homi Bhabha himself, which shows you the kind of company and this thing, kind of reputation he enjoyed in the international community. But he spent most of his career, taking that forward to build up science and technology in our country. And our country owes a lot to Homi Bhabha, and that's one reason I think we are very delighted to, remember him every year with this Homi Bhabha Memorial Lecture. And this is a quote, and which essentially tells you why people actually do basic sciences in addition to applied sciences. And that's because, there is that unfettered challenges that you want to face, which may not sound practical, but they are the ones which lead technology into new domains. So with that, let me come to today's speaker, Yashwant Gupta, who will be talking about probing the universe with radio waves. And so Yashwant graduated as an electrical engineer from IIT Kanpur in 1985. And he, again, is amongst the engineer scientists of the country. He did a PhD, an MS and PhD in radio astronomy from the University of California, San Diego in 1990. And soon, very soon after that, came and joined what was still probably not called the National Center for Radio Astronomy. It was called the GMRT. And I remember I was just a new graduate student in IUCA hearing hushed murmurs about how Professor Govind Sarup had netted a big fish. And we were all looking forward to seeing this very young, handsome and bright couple who had come to this campus. And he's been there since and has really proved Govind's claim right. He's been the leader of the field. He's won the Shanti Swarup Bhatnagar Award. He's been recognized by the academies. And he has now has a very important role of being the center director of the National Center for Radio Astronomy, which runs world's largest radio telescope in its frequency bands, the Giant Meter Wave Radio Telescope, which is 80 kilometers away from here. If students haven't seen it, I really invite you to see it. I mean, it is breathtaking to see its science being done at such scales. And you should definitely arrange for trips there. And he also is leading India's efforts in contributing to the square kilometer array, which is, sort of the largest radio telescope ever in the world, being set up partly in in Australia and in South Africa, between two continents. And NCRA leads, and NCRA and in particular Yashwant from there leads India's contribution to this major global effort. With these words, let me welcome Yashwant again and invite him to give his presentation. Thank you.
Well, thank you, Tarun. And it's a real pleasure and also a very big privilege for me to be here today amongst all of you to deliver this lecture. And I think it's a special privilege because it is the Homi Bhabha Memorial Lecture, and I work in an institute which was founded by him. And as we've already heard about his major contribution to the growth of Indian science and also technology. And so it's all the more a great pleasure to be here. So what I'm going to talk to you about is how we probe the universe with radio waves. And as we make this journey, I'll really start, so this talk is in few parts, I won't tell you how many. If you get too bored or too tired, I'll cut off the last few parts, but let's see how far we get. But we'll start right from the beginning. So when, and it's for no reason that astronomy is called the oldest science, because ever since man settled down and was able to earn his, earn his bread, so to speak, his attention was drawn to the heavens to try and understand what's up there. And of course, it started with the use of naked eyes, because that's where the natural detectors for light waves reside, and all the signal processing, of course, in the human brain. But this evolved dramatically, took a quantum jump when this man, Galileo, first turned the newly invented optical telescope to the heavens, and that revolutionized astronomy forever. And of course, started with simple discoveries, but then if you trace the growth of the optical telescopes through the ages. So we start with this replica of Galileo's telescope to something that Newton built and used, to what Herschel used, and then we go on to the large big observatories of the world, the Mount Wilson telescope, the famous Palomar telescope, and then you see these giant behemoths which are today's modern optical telescopes with mirror diameters which are tens of meters. And so what comes through straight away in this is that bigger is better. And you would say, well, that's obvious, but let's just take a moment to understand why bigger is better. And there are two main reasons. The first, I think most of you understand, and I'm sure many of you understand the second one also. The first is just that the bigger the telescope, the more light it collects, and therefore more sensitive it is, which means that if there are fainter objects out there, it will detect them more easily, right? That is what we call sensitivity. But we also know that any aperture or a telescope has what is called a resolution, which is the ability to distinguish sources at nearby angles in the sky, right? And that resolution depends upon the size of the aperture. This comes from the standard diffraction theory. And so it turns out that the resolution goes as the wavelength of the radiation divided by the size of the telescope, the aperture, and the sensitivity goes as the collecting area, therefore as the square of the diameter of the aperture. So this tells you that the bigger the diameter of the telescope, you get sensitivity going as square of that, and you get a finer and finer resolution, which means that it can distinguish objects which are closer and closer in the sky in angular separation, right? And so we'll just illustrate that with a couple of examples, starting with our nearby neighbor, the moon. So if you look at the moon with the naked eye, this is what you see. And when you start looking at it with simple telescopes and with bigger telescopes, now you can see the difference. In terms of resolution, you can now make out finer details. and in terms of sensitivity, you can make out fainter things. And if that is not convincing, we'll see in the next example, where we'll go to our nearby galaxy now, the Andromeda galaxy, which some of you who are amateur astronomers would have even tried to look for, because with the naked eye on clear skies, you can just see it as a small fuzzy patch. Okay, it's out there in the constellation of Andromeda. And so this is what it looks like when you look at it with different optical telescopes. So with a small, with the naked eye in very good conditions, you may see this. And then as you start putting bigger and bigger telescopes, this is what happens. And again, so what you see is two things: fainter objects become visible, and you can start resolving and seeing the detailed structure of the object, right? So those are the two driving forces, and as we'll come back and have to revisit this when we go to radio. So now we come to the next part, which is what happens beyond optical wavelengths. So as I said, this whole thing started because our eyes can detect optical waves, but as we all know that light is just one small part of a very large electromagnetic spectrum spanning a huge range of frequencies or wavelengths, and all the way from radio waves to gamma rays. And the simple question, of course, then one would ask is, can we see radiation from objects in the universe at these different wavelengths? Do they emit? And if so, can we learn something new or different? And so that leads us to the simple question that, can the same object be studied at different wavelengths of the electromagnetic spectrum? And you would say yes. The simple answer is yes. If it is emitting, you should be able to study it. And do the different wavelengths give us different information about the object? And that's an interesting question, and we'll see pretty soon that the answer is again yes. And can some objects or phenomena be studied only at some wavelengths? And that is an interesting question, and that also has the answer yes. So there are certain objects which will, for example, not emit optical waves, or if they do, very faint, but they may be very strong in ultraviolet or in gamma rays or whatever. And so if you did not have access to these other wavelengths, you would never learn about these objects, and we'll see some such objects as we go along. So that would then motivate one. So here's one example to show this. So we are back to our nearby friend, the Andromeda galaxy, and this is an image of the galaxy made in different parts of the electromagnetic spectrum. And we won't get into how all this was obtained, but what it shows is the points that I illustrated, that yes, you can see the galaxy at different wavelengths, and yes, the different wavelengths tell you different things. So different parts of the galaxy are more prominent at different wavelengths, and you can see that there are certain parts which are seen only at some wavelengths and not seen at other wavelengths. Okay, and I'll leave that for you to spot, but you can easily see that. Okay, so this then brings us to the question that can we do this, and how was this done? And that poses two issues. One was this fact that we had the natural detectors, which is our eyes, to detect it, and you have to ask, where are the detectors to detect the other wavelengths? And the other is this question which you may think, may not have thought about, but do all these wavelengths reach us? Okay, and so as I said, the first part is that you need to have detectors, and that's where technology comes in. So you need to find the right kind of device that is capable of detecting these things. And then, as you know, technology has evolved significantly: photographic plates, charge coupled devices, radio communication equipment, and so on, which has all enabled all this to happen. But this problem, which we should be aware of from the ozone layer and the ozone hole that we know about, that the ultraviolet from the sun does not reach us because the ozone layer blocks it. And once you think about that, you can imagine that different parts of the Earth's atmosphere or the ionosphere may block or obstruct different wavelengths, and that actually is true. So what this shows is what is called the opacity diagram. That is, how opaque is the Earth's environment to different electromagnetic waves, spanning again the whole gamut from gamma rays to the lowest frequency radio waves. And what you see is that what we have found is that, yes, there is a well-known optical window, which is why we get optical signals reaching all the way onto the surface of the Earth. But other than that, there's only this one big window which happens to lie in the radio frequency part of the spectrum, where the waves can actually reach the surface. In other places, they are blocked for a variety of reasons, ranging from simple absorption or reflection of the very low frequency radio waves by the Earth's ionosphere to absorption by various molecules in the Earth's atmosphere for different specific wavelengths, and so on. So that then would say, well, if any other branch of astronomy would have evolved after optical astronomy, it should be radio astronomy, because that is the one where you don't have to do too much effort as long as you can figure out what the detector should be to detect those waves. You can get going. For the others, we had to wait till we learned how to fly telescopes on either high altitude aircrafts or on spacecrafts well above the Earth's obstructing layers to be able to probe the universe at those wavelengths. We won't go there, so we will try and move towards radio waves. So it's interesting to trace the early history, because this is where we come to realize the contribution made by J.C. Bose. But as you all know, Maxwell developed the theory that predicted that electromagnetic radiation would exist at all wavelengths, including radio waves. And it was Hertz who actually proved that the waves predicted by Maxwell do indeed exist, and by a demonstration. But when he was asked about what use would these be, he dismissed them as being of no practical use. But it took people like J.C. Bose and then Marconi to actually generate, that means transmit and receive these waves in a controlled fashion. So J.C. Bose was the first person who showed, and at a very high radio frequency of 60 gigahertz, that how can you generate them and how can you receive them and then use them to do things. But then again, he also took it more as a scientific curiosity, and he did not really believe in patenting it and thinking that this could be built into something much more. And it was then Marconi who picked up that thread, and he went on to patent this whole business and worked on developing the first radio telegraphy sets, whereby then people realized that you can use these waves for communicating and talking over long distances. And that's how the whole field of radio communications and radio engineering started and has grown to the way we know it today. But from there, you would have asked, well, how long before actually people could say, well, I've got signals at radio wavelengths coming from outside, and that was another 30 years or so. And that is because, again, there was no expectation that there would be radio signals coming from celestial objects, and there was really nobody looking. And so therefore, so this is just my tribute to J.C. Bose for his pioneering work, which actually we have a replica of his setup, the experimental setup at the GMRT. So if you visit sometime, a request for that to have a look at that. And so we come to the actual genesis of radio astronomy, and as it often happens, it was a serendipitous discovery. As I said, people were not expecting to detect radio waves coming from celestial objects, and the origin lies in the Bell Labs. So obviously the detectors, as we discussed, were already there, but they were being used for man-made communication. And so at some point when they got to the stage of trying to do transatlantic communication between Europe and the US, they found that some of the equipment was giving trouble. It was not working to the expectations. There was unwanted noise or hiss in the equipment, which was corrupting the real signal that they wanted to transmit. And so this gentleman called Karl Jansky, who was an engineer at Bell Labs, was given the task to try and find out that why is the transatlantic communication equipment misbehaving. And so in order to understand where this unwanted disturbing signal was coming from, he built this interesting looking contraption, which is actually a radio antenna mounted on these wheels so that you can turn it, rotate it, and look at different directions and try to find out where this unwanted interference signal is coming from. And to his surprise, he found that it was not coming from any terrestrial source, but was coming from some fixed direction in the sky, as shown by this simple chart record. And so whenever the antenna was pointed in that direction of the sky, he would pick up a signal. And that was then the realization that what you're seeing are radio waves coming from somewhere out there, rather than something man-made or any other source on the Earth. And so that was about 1936. The frequency was a very low frequency, 20.5 megahertz. And from there, the realization came. But initially, astronomers who were very active in optical astronomy were still very skeptic about what could be done or learned using radio waves. So all the early pioneering work was done by good old-fashioned electrical engineers who worked on these systems as hobby. So this is Grote Reber, who is one of the pioneers, again an engineer in Bell Lab, who in his spare time in his backyard built this contraption, which now looks more like what you think of a radio antenna. And he used this operating at 160 megahertz and mapped the sky to make, what is the first radio map of the sky. And what people started finding very soon, and which is where we will move to, so what he could see is all the bright sources in the sky, and as you can see, he could see that most of the radiation is confined to this belt, and it's probably not too hard for you to guess that as is the plane of the Milky Way galaxy that is being picked up as the most of the radiation coming from our galaxy. And this is actually the center, direction to the center of the galaxy, which is the bumps that Jansky was seeing in his equipment. So that takes us to the next stage, that what is it that is different that the radio waves reveal compared to the optical. And this became very quickly, in the early days, people became aware that what we are seeing is a complementary view of the universe. So the brightest radio sources did not have any significant optical counterparts, and vice versa. And so clearly people were onto something new and different. So this is an example. I won't dwell on it, but just to point out that the reason is, of course, that the physical processes giving rise to radio emissions can be and are quite different from those giving rise to optical. And hence, sources look very different in the radio and in the optical. And also, of course, in the early days, the resolution of optical telescopes was very poor, and we'll come back to that in a short while. But that slowly improved. So it's a time to step back and ask, well, what are the kinds of physical processes that you would expect to produce electromagnetic radio waves? And the simplest one, I think, that many of you would relate to is that any accelerated charged particle radiates, right? And so you can ask, in what are the different ways in which you can accelerate charged particles out there in the universe, whether it be in a nebula or in a galaxy or in a star. And there are two main ways. One which is when you have positive and negative charged particles in a gas, and then as they are zipping around, they undergo acceleration, and you can get the accelerated charged particle to radiate. And this is what is called thermal radiation. It's also called free or Bremsstrahlung. And this is very common. Wherever you have ionized gas, you will see this kind of effect. The other, which is non-thermal in nature, and the closest analogy of that we know is synchrotron, that whenever you have charged particles along with the magnetic field, then for example, if the electron is gyrating around the magnetic field, then it will emit radiation, and the radiation can be beamed, and it will be more beamed the higher is the speed of motion of the electron. And this is something again that is very commonly seen. So these are two examples, but if you go beyond this, there are other ways. So, but this itself brings us to the point that if you look at the emission from our galaxy in overall, this is what our galaxy looks like in the optical wavelengths, and this is what it looks like in the radio wavelengths. So this is, you look around and you reconstruct what the view of the galaxy would look like, and as you can see, there's a dramatic difference, and that's because what happens is that these charged particles can move out to large distances away from the plane of the galaxy, and there are magnetic fields in all of these regions, and then you get a lot of synchrotron radiation, though predominantly from the disk, but also from other places, whereas this is dominated by stars and objects of that kind, which are primarily confined to the plane of the galaxy. So, but there is other interesting stuff, and the one that again most of us are familiar with is that whenever you have an atom or a molecule transiting between two energy levels, you either absorb or emit radiation, and this is what leads to the phenomena of spectral lines. So you will see a narrow emission or absorption in the spectrum corresponding to the delta E equal to h nu relationship for that particular difference in the energy level. And when you couple this with the fact that hydrogen is the most abundant element in the universe by far, and you ask, well, what is the way in which I can probe neutral hydrogen? So neutral hydrogen is very simple. It's just a proton and an electron, and you ask, well, how do I detect its presence? And so it turns out that the proton and the electron can have their spins parallel or anti-parallel, and these two different states have a small energy difference. That energy difference, delta E equal to h nu, gives you the nu at 1420 megahertz, which is 21 centimeters, and this turns out is the only way in which you can detect the presence of neutral hydrogen gas directly. And there are indirect ways of doing this, and as you can see, that is the frequency which lies bang in the middle of the radio window. And so you won't see this in optical, you won't see this in any other part of the spectrum. And even in radio, you will just, when the atom is at rest, you will see it only at that frequency. And so now you can start to appreciate the power that different branches of astronomy can bring. And when you couple this further with the fact that if that atom is not at rest but is moving, then that frequency will be Doppler shifted by the well-known Doppler effect. And so it will be red shifted if the atom is moving away from us, it will be blue shifted if it is moving towards us. And then you couple that with one more thing that is well established, which is the expanding universe and Hubble's law, which says that further away objects, that everything is receding from us, and further away objects are receding at faster speeds. Then it tells you that further away is a cloud of hydrogen gas, the more Doppler shifted will be the hydrogen line that you will see from it, right? And so this, what then tells you is that if you don't see the line at this frequency, but you see it at some other frequency, then you can then figure out effectively how far that object is, which is what is traditionally called redshift in our jargon, using the relationship with Hubble's law. And this then allows you to actually probe the universe in distance. And when you probe it in distance, given the fact that there's a finite travel time for electromagnetic radiation, you're actually probing the universe in time, back in history. So now with this chain of reasoning and this very simple observation, which requires you to use your radio telescope to see if you can detect this line, you can do a huge amount of study of the universe and learn about things which are quite amazing. And so this actually provides one of the most powerful tools to probe the universe at different epochs of evolution. And I won't have too much time to talk in detail about it. But in addition to this, there are still other mechanisms whereby you can get radio emission. And so you all know the black body spectrum, that any object will have some amount of black body emission even at radio wavelengths. Even the sun, which peaks at optical, will have a small amount of thermal black body radio. But the sun has radio radiation from some of these other mechanisms that I talked about, which is much stronger. So when you look at the sun in radio, you don't see the thermal emission, the black body emission. You see all the other non-thermal stuff, which tells you a different story about what's happening in the outer layers of the sun. And then there is various kinds of plasma emission mechanisms, including masers. So we all know about lasers, and maser is nothing but the microwave frequency equivalent of the laser. So and so you can have situations where the radio radiation can be amplified, just like a laser radiation is amplified. And such objects or clouds do exist out there in the universe, where you get very strong mazed emission in radio, and you can actually look at some of these objects. And I'll just, so this is one example which just shows you again the difference. So this is an image in optical, shows a galaxy, it shows another galaxy, maybe another galaxy, and so on. It's just it's a field out there. When you look at the same field in radio, in the 21 centimeter signal, you see this kind of a picture. It tells you that, well, this galaxy and this galaxy are not unrelated, which you can't make out by looking at this. They're actually talking to each other. They're gravitationally connected. There's material flowing from one to the other. And similarly, this galaxy is also coupled. And the moment you can measure a redshift, you can then work out how far they are from us, and so on. You can also measure how a galaxy is rotating. So if the disk is rotating and it is tilted at some angle to you, then some part of the disk will be coming towards you, other part of the disk will be going away from you. And if you look at the hydrogen gas in these two parts of the disk, you will see that it is blue shifted and red shifted with respect to the mean velocity. So this is a diagram literally showing the color of the shift from blue to red, and then you can actually work out how the galaxy is rotating and work out the dynamics. And that's how dark matter is discovered and inferred by studying such rotation curves of galaxies. Okay, then I'll come to the kind of object which I work on, which is what I call pulsars or neutron stars. And these are very amazing objects. They are stars which are made up only of neutrons, and you can ask, how does that happen? We don't have time to go into the story of that, but it comes from the collapse of the core of a star in a supernova explosion, and that core compresses the star down to an object which is about 10 kilometers in size, and it consists primarily of just neutrons, just nuclear density matter. So the atoms and molecules have been crushed, and there is only nuclear density matter. So you can imagine as much mass as the sun packed into a 10-kilometer size ball, and these rotate quite rapidly from few times in a second to more than 500 times in a second. So you can have these objects smaller than the size of Pune, containing as much mass as our sun, and spinning faster than most of your typical motors would rotate. And they are extremely interesting objects because they have very extreme properties. As you can imagine, if you put a mass of the size of the sun at 10 kilometers, then if you were 100 kilometers away from it, the gravitational force would be amazing, right? And similarly, they have very strong magnetic fields. So all kinds of interesting phenomena happen in their surface and in their magnetospheres. But what is more interesting is that they are like lighthouses. So they have strong radio emission beams coming from the two poles of the magnetic axis, which is predominantly a dipolar magnetic field, and that axis is misaligned to the rotation axis. So the star is rotating on the axis which is parallel to this to the board here, and the magnetic field dipole is misoriented, and the beams are coming from the two poles. And as this sweeps by, if the line of sight cuts the beam, you see a bright flash of radio pulse, radio emission, like a pulse, just like when you see a lighthouse which is spinning around. And so the signature that we get are repeating pulses of radio emission, and as I said, they can come at the rate which is once a second to once in 1.5 milliseconds or so. And so you can imagine that if you want to capture data from such an object, what kind of equipment you have to build connecting to your radio telescope. But we won't get into those kind of details. And over the years, it's been now 50 years since the first pulsar was discovered. We've found more than 2,000 pulsars so far, out of about 100,000 that are predicted to exist in our galaxy. And they come in all kinds of variety. And they're excellent tests of physics in extreme conditions. There's at least a couple of Nobel Prizes which are associated. In fact, today there's a big thing about gravitational waves. The first demonstration that gravitational waves are emitted was shown from studying a binary pulsar and working out how the binary pulsar orbit of two neutron stars was shrinking because of the loss of energy in terms of as gravitational waves going out. And that was 2003 when the Nobel Prize was given, and the work was done from 1970s onwards. 20 years of continuously studying the pulsar to get that kind of inference. But there are much more that you can do in addition to just trying to understand the physics of what produces this emission. So like, it's coherent emission. It has all the properties of, the laser and the maser kind of stuff. But much more than that, in fact, we still don't understand exactly how they work. And then we'll just move very quickly to what are called radio galaxies. So, you have this picture of this galaxy, which is this nice spinning wheel that you may or may not indulge in day after tomorrow. But when you look at the some of the galaxies in radio, they look completely different. And this again is telling you that you're tracing a different physical phenomena in the universe. So this is an example of a radio galaxy where the actual optical counterpart of this galaxy may be just a small object over here. So what's happening is, for some reasons which are actually related to the supermassive black hole which resides at the center of these galaxies, there are very highly energetic jets of relativistic plasma that is thrown out from the central engine, and that then energizes the surrounding medium and makes it glow. And this is something, obviously, if you look at an optical image of this, it would just not show up. It would look completely different. So, having made this point that there is a completely different view of the universe that you can get from this, we just come back and say, well, how is this done? What do you need to do? Because we left that story at the point where just the detectors were just found, and Jansky and Reber just did the first radio observations. But how does a modern radio telescope work? And in a very simple sense, it's no different from your basic satellite dish, in the sense that there's a parabolic reflecting surface which focuses incoming radio waves to a focal point where it's converted to electrical voltage. The voltage is amplified, detected, and then you get your useful information out of it, which is your favorite TV channel or whatever it is. Okay, that's how it works. Except that the signals that we are looking at are much, much weaker than what your satellite, man-made satellite, is beaming down to you. And those are so weak that they have their own special units. So one Jansky, in honor of Carl Jansky, 10 to the minus 26 watts per square meter per hertz. And you say, well, what does that mean? If you're an electrical engineer, that's a power of minus 100 dBm coming into a typical radio telescope. And what's minus 100 dBm? 0 dBm is 1 milliwatt, and the dBm is a log scale. And so you do minus 100 dB down from 0 from 1 milliwatt. If you still don't get that, then if you run a typical radio telescope for 1,000 years of continuous operation and collect that energy, it's about a millijoule. So you spend much more than that in just heating up your morning cup of water for your tea. Okay, so what you should realize is that how does the radio astronomer then extract the information that he wants from this very, very weak signal? So what you have to do is, of course, you say something is very weak, just amplify it, right, till it becomes loud enough that you can see it, right? That's easier said than done, because when you try to amplify something, you use electronics. And all electronics has intrinsic noise. And that, again, some of you may have read and come across. So if you build a simplest transistor device, it will have its own intrinsic noise. And that intrinsic noise will often be much stronger than the strength of the signal. So if you amplify, you will amplify the noise as well as your signal. So unless you can beat that basic problem of having enough signal to noise, you can't just blindly amplify. So what you have to do is you have to just collect more of that signal, that very weak signal which is coming. So a couple of feet wide dish will not do. So what people end up doing is make antennas which are several tens of meters in diameter, as large as possible. And then in order to beat the noise problem, you go and work on the technology of how you can make electronics with very low noise. And it's possible to do that. In the extreme cases, you have to cool the electronics device in a cryogenic receiver down to some minus so many degrees, so that the intrinsic noise can be suppressed to a significant amount. Finally, we make use of the fact that much of this natural phenomena, except for the spectral lines, which have a very narrow extent in frequency, much of this natural phenomena occurs over a very wide range of frequencies. And so therefore, if you can observe over a large bandwidth, then you can collect more in hertz, then this quantity will go up. So either you increase the meter square or you increase the number of hertz over which you're collecting the signal, then you'll get more watts. Finally, in the end, most of these sources, by and large, are static. So if you go look at it now, look at it 5 minutes later, look at it tomorrow, it will give you the same signal statistically. So you can then integrate the signal over longer and longer durations. And when you integrate, noise which has a random property will reduce in its amount of fluctuation, and the signal will build up. And so this is another way of enhancing the signal to noise when you cannot do much better in any of these other parameters. So you try and observe as long as possible. Of course, there are some sources, like you saw the pulsar, where it is not a constant source. So there are pulses coming in. If you want to examine each pulse in detail, then you can't integrate otherwise people integrate from minutes to hours to days in order to increase the signal to noise. So that leads us to this basic question, that how do you describe a basic radio antenna? So when you have an antenna, it's picking up radiation coming from a given direction, but no antenna can pick up only one direction. It picks up usually over a range of angles. It will accept a small range of angles, which again is the resolution of that antenna. That range is again lambda by d, where lambda is the wavelength and d is the diameter of the antenna, because it will not be able to distinguish radiation coming from a small range of angles. It picks all of them. And then it has to be mounted on a platform where you can rotate it if you want really to look at different parts of the sky. And these are typically two-axis motion, as is in most typical telescopes. And finally, what happens then is that, as I said, now we are back to our first few slides where the sensitivity went as d square and the resolution went as lambda by d. So now we have this problem that the lambda for us is much, much larger than optical wavelengths, right? We're talking about wavelengths which are of the order of meters, whereas there we were talking about wavelengths which were in thousands or hundreds of nanometers. And so what happens is this problem, that even if you build a 100-meter size antenna, the lambda by d turns out to be half a degree. And what is half a degree? Half a degree is 30 arc minutes. It's the angular size of the sun It's also the angular size of the moon, and so on. So what that means? That means that if you build a 100-meter size antenna and looked at the moon, instead of seeing the moon like this, you would see it like this. You would not be able to resolve the details even across the surface of the moon. So that's a very poor low resolution telescope. So this is an example of what a low resolution telescope would show looking at this galaxy with a higher resolution. So you are way behind the optical astronomers, and you say, well, can I compare the same object? I can't, because I'm seeing it with much more blurry eyes than what the optical guys are able to look at. And so this was a big challenge, and so you build bigger antennas, but it's not practical to build something, you know, hundreds of meters and steerable and moving and so on. You end up with fixed antennas like this, where you can't move the antenna. You can just have some limited coverage as the source, as the Earth rotates and the source crosses the field of view of the antenna for a few minutes. So this problem was solved by understanding that you can actually synthesize a much larger aperture as far as the resolution is concerned by combining the signals from many smaller antennas located at large distances. Okay, so this is an example where you can see now many antennas of reasonable size but spread out over long distances. And here you can show that the resolution that this array will give you is now lambda by ds, where ds is now the largest separation between the antennas rather than the individual aperture of an antenna. And this, this technique with some refinements is what is called Earth rotation aperture synthesis. I won't have time to go into detail. I'll show you in the next slide just the physical basis for this. But this was the technique discovered by Sir Martin Ryle, who again got a Nobel Prize for this. And it allowed radio astronomy to actually compete with the other fields of astronomy in terms of being able to study the same object with similar kind of resolution, so you can actually compare and extract the maximum physics out of what's happening in the object. And so in order to understand this, you can, what is done is that you take the signal from every pair of antennas and cross-correlate it. Okay, and if you are scared about the jargon of what's happening, the simple way to think about this is you've all studied the Young's double slit. So in a Young's double slit, when you look at it, you get a sinusoidal oscillation of the pattern produced, which is just the interference pattern between the sources of the two slits. And what it tells you is that two such apertures actually correspond to a sinusoidal response on the sky. And this is coupled with one extra piece of information which is called the reciprocity theorem, which says that if you transmit from two antennas and they produce an electric field which is an oscillatory response, then if there is a source with such an oscillatory distribution of electric field, you will get maximal signal response from this pair of antennas when you combine the signal from these two antennas. Okay, this just comes from reciprocity. And so what this then tells you is, and as you know that as you change the fringe, the spacing between the slits, the spacing of the fringe changes, right? And for those of you who studied Fourier transforms, it actually what you're doing is you're measuring one Fourier component of the distribution of the brightness on the screen. Okay, so as you change the slit spacing, you are actually picking out different Fourier components of the image. So this Fourier decomposition is not a temporal Fourier decomposition, which is what we are used to. This is a spatial Fourier transform. You are transforming the spatial dimension, and in the most general case, we'll be transforming two-dimensional. So because most of the times when we are making these images, these are two-dimensional distribution of intensity in space, and you're actually doing a two-dimensional Fourier transform. And what you're doing is with every different pair of antennas which is located at different spacing, you're actually measuring one Fourier component of the image. And then you assemble all the Fourier components, and then you do an inverse Fourier transform to get the image. It's not as simple as that, but that's the basic idea. There are complications because you'll see immediately that, look, how many Fourier components did you measure? If you had n antennas, you'll measure NC2 combinations taking pairwise. that is not the full information in the Fourier domain. How did you reconstruct the image? I won't go into the details of that, but it has been shown that you can actually do this and recover sensible images of the objects in the sky. And just to demonstrate this, we are back to that radio galaxy whose image I showed you in that assemblage of radio galaxies. And this was an image made in the old days before this interferometry technique, aperture synthesis, was invented. And this is image of the same radio galaxy made with the more modern instrument. Again, so you can see the difference in the resolution, where you can now pick up much finer detail. Of course, the difference being that one is a contour plot, the other is a grayscale. But apart from that, you can see the power of higher resolution obtained by making these large arrays. Okay, so what we'll do now is to maybe the last part, which is the growth of radio astronomy in India, and with a case study of our own GMRT. And as I said, this is the occasion to point out Homi Bhabha's contribution to the growth of radio astronomy. And as founder of the institute, he had the foresight to realize that this is an emerging new field, and he invited Govind Swarup to return from the US and set up a group at TIFR in this field, which group has grown and is now today the National Center for Radio Astrophysics. And he provided unstinted support. So just like Tarun said, he had supporters who supported him. He supported the youngsters who came and worked, and gave them freedom to go try bold new ideas. And as a result of it, the first telescope in India, radio telescope, the Kalyan telescope, located in Kalyan, yes, the Kalyan that you all know about, where you will not be able to build a radio telescope today, and then the Uti radio telescope, and a new branch of science. So this is the historical letter in 1962 or whatever, inviting Govind Swarup to come back and set up a group. And so, like I said, this was the first telescope built in India back in the early 60s. But the most important one after that was the Uti radio telescope, built in the 1970s, which is still actually working, and we use it for doing cutting-edge science even today. And then the giant meter wave radio telescope, which was completed in the late 80s to the early 90s and made operational, in the late 90s to early 2000 and made operational in 2002. And it was Govind Swarup who started all of this. So the GMRT is primarily a low frequency instrument. Works from about 100 megahertz to 1450, and you may realize the importance of that when you couple this with that 1420 megahertz that I talked about, and the fact that most of the universe is redshifted from us. So it was really designed to probe the universe by looking at the H1 going just down from 1450 as far as you could allow with the technology. And it has 30 antennas in an array. Each antenna is quite large, 45 meters by itself, and spread out over a 30-kilometer region. I'll show you in a minute. And it was designed, built completely in-house in the country by our group. And more recently, in the last 5 to 6 years, we completed a major upgrade after it was running for 15 years or so, which upgrade gives it much higher sensitivity and almost continuous frequency coverage over this entire band, and makes it a much more powerful and versatile facility. So this is what the array looks like. So as Tarun said, you should take the effort to make a trip, and we welcome visitors. Every Friday is a visitors day, that's like today, and there's official visiting slots where people can visit, and there are people designated to show them around, but even otherwise at other times one can organize visits. And so that's the location. Like I said, so this allows you to synthesize almost a 28-kilometer size radio antenna by combining the signals from all of these. And so today you have to Google everything. If you Google, this is what it will show you, an image of the central square compact region, which has 14 of the antennas. You can zoom this, you can start seeing the individual antennas. So these are the three closest. As you can imagine, when you do that NC2 combination, you want different baselines. So you spread the antennas out so that you can get short spacings, medium spacings, long spacings, all different Fourier components can be then recorded. So this is the main building where all the signals come over optical fiber from the antennas, and then there's a lot of digital electronics to do all that stuff that I showed you in that one single slide. Control room from where everything is run and operated, and guest house and other facilities over there. It's just another view from a nearby hill showing the array. So now you can understand what 45-meter means, and so this is a 32-meter long crane which is needed in order to access the most sensitive electronics, the first amplifiers and all that, which sit right at the focus where the signal is converted first to a voltage. You'll also notice that this looks like a transparent antenna. It's not transparent. There's a very fine mesh which acts like the reflecting surface, and that's good enough to reflect the frequencies that we are working at, which are from centimeters down to meters, and you can work that out as to what kind of a metal surface do you need in order to reflect a radio wave of a certain wavelength. You need to be lambda by 20, not finer than lambda by 20 to act like a good reflector. This is just a shot showing how the single antenna was built. So that's a 3-story building equivalent height cement tower on which the antenna sits, and there's a big rotating bearing here which rotates the whole antenna in azimuth, and then it's mounted on this yoke with a structure which allows it to rotate in elevation, and so the final assembled dish can go down to 17 degrees to the horizon, and all the way, of course, to 90 degrees and beyond, and it can go around plus minus 270 degrees to cover pretty much the whole sky. And so as you can begin to imagine that if you want to put together something like this, there are all kinds of engineering that is needed, all the way from the mechanical system to the precision with which you move this heavy 100-ton structure so that it can follow objects as the Earth rotates slowly. And then that's again a precision servo system. And then the rest of it is the actual electronics from radio frequency feeds to pick up the signals at different frequencies, to transmit them down, optical fiber technology to transport it up to 2 gigahertz of bandwidth on the analog transmission, and then finally to digitize that and then process it. That's something like a 20 teraflops of computing required to do that, and it's real time. It's running all the time when you're doing an observation of a long sequence. And then the entire monitor control telemetry to be able to do all this in an automated fashion sitting in the control room, and then the actual software for managing the entire observatory, and then the software for actually processing the data that you get, all that business of actually doing the Fourier transforms, making the images, and getting the best quality results. So you can see there's a whole range of stuff that we work with. And so this is when it was completed, like I said, around the end of 2001. It was available as a international facility from early 2002, and it sees users from all over the world pretty much, with a healthy in-house participation from the country, about 50%, and it's typically oversubscribed, which means that the requests for time for scheduling experiments is about 2.5 to 3 times more than the actual time that we have in any 6-month cycle for scheduling. So that means competition, which means only the best proposals for the best experiments get time on the telescope. Okay, so what does it do? It is a lot of what I already described, the various kinds of ways of studying the universe with radio waves. So I won't go into the details, but you can study the sun. You can even try to look for extrasolar planets using possible radio emissions from extrasolar planets. Pulsars, which I talked about, different kinds of galactic objects, supernova remnants, and so on. And lots of these explosive, today the universe is known to have lots of these explosive events, whether it is gamma ray bursts and other kinds of explosions, and a lot of those can be traced with radio signals. And then the hydrogen gas that I talked about in our galaxy and all the way out to distant universe, radio galaxies that I talked about, and even all the way to the early universe, the cosmology and the epoch of ionization as to when the universe was first stars and first galaxies formed in the universe. And you can also make an all-sky atlas of what the universe looks like at a given frequency. Just like you use an atlas to refer for various things, you can go and refer to it for understanding various aspects. So I won't go into the details of this, and I think this is the part probably I should stop given the time, unless people are interested. I can, so that's why I was going to ask you that if you're interested. So this is just looking ahead, just maybe 4 or 5 slides. So we talked about GMRT, we talked about how we upgraded it and made it into a next generation facility, but there are radio telescopes coming up all over the world, both at low frequencies and at high frequencies in the millimeter wave spectrum. And the one that we are all sort of looking to eagerly is the square kilometer array, which Tarun mentioned in the introduction. And so this is like the growth chart of radio astronomy from growth reverse time, plotting the sensitivity of a new generation of radio telescopes as a function of time. And on this chart, when GMRT was built, it sits here. The upgraded GMRT probably sits somewhere here. And the time axis is slightly out of sync. The SKA, when it's built, which is beyond this current time axis, will actually be 30 to 50 times more sensitive than any radio facility that exists, in its full form. So it will have 30 times the total collecting area of GMRT. So if you were to do it with GMRT sliced dishes, there would be 30 into 3900 dishes, but it will have smaller dishes for other technical reasons, so 3000 dishes in the final configuration and the dishes, we are talking about 30 kilometers. The talk there is to go to 1000 kilometers kind of extent of the array. And of course, all still connected with optical fiber for real time, bringing the signals back. A much wider frequency range of coverage than what we do at GMRT. And most importantly, located in regions. So one of the biggest problems for radio astronomers is man-made noise. So that same mobile phone that you cannot live without is a terror for us, because the mobile tower transmits, like you understood earlier, that the power that the mobile tower transmits is millions of times stronger than the level of signal that we're looking for, and that easily can corrupt the signal we're looking for. Actually, it can saturate the entire receiver system, make it nonlinear, after which it doesn't make any sense, the data. So you need to go away from where man-made noise is. And so these are regions in the edge of the Western Australia desert and in South Africa in the northern part, where they count people as 1 person per square kilometer or half person per square kilometer as the human density. And but still not so far that you can't take power, electricity, and all the various things that you need in order to run such things. But the aim is to do cutting edge science. It is split in 2 phases. The full SKA, which I talked about, is really a humongous exercise. SKA phase 1 is a smaller version of it, which is currently in the design phase. We'll start construction by 2021 and should be ready by 2026 or 27. And I won't go again into the details. It's just that the technology barrier or the frontier it pushes is right at the cutting edge. I mean, the total data traffic over the optical fiber network will be more than the total internet traffic that you have today in the whole globe. That's just the data coming back from the antennas, and you have to process it. And so you need heavy duty processing, the best supercomputing capability in order to process the data and so on. And you can imagine the whole system to manage the telescope would be again a big thing, because it's a vast distributed network of antennas and in 2 different continents at that. So this phase 1, which is a smaller version, has a limited scope, lower frequency coverage, the smaller extent of the array, but designed so that you can expand it later and grow it. So it has these 2 sites and a global headquarters in the UK in a place called Jodrell, which hosts one of the early large single dish antennas. And this is now completing design at the end of this year. Early next year it will be finished, and by late 2020, early 2021 it will start construction. As you can see, these are not simple or cheap things to build, and therefore it requires many countries to come together. So this is where it will be located in South Africa, in the northern part of the country. And the data has to be taken all the way to this nearest places, Cape Town, 800 kilometers over fiber links. And the first phase will have about 200 dishes spread out over 150 kilometers. And in the Western Australia, So that will work at the higher frequencies and the lower frequencies. So now you can see this is a different design. So these are just dipole antennas. These are no longer dishes, and you can actually make an antenna by combining signals from many dipoles, the field of dipoles, and combine them and make it work like an antenna. And the reasons why it's done are technical, but it works better at low frequencies. So the very low frequencies from 50 megahertz to 300 will be done in this manner, again located in a quiet place in Western Australia. And so this is the global collaboration. These are the current member countries. The others who are interested, and some have already sort of joined. Portugal has joined. Germany is also close to joining. Maybe Switzerland soon. And they all working together towards this common goal. And the science, as you can imagine, is really transformational, all the way from the cosmic dawn, which is that the first. The hope here is that you will be able to image in radio the very first stars and galaxies as they formed that far back, about almost 13 billion years ago in the universe. And from there all the way to various kinds of things, including very hi-fi tests of theory of gravity, fundamental physics, and more interesting things which I didn't quite talk about. But when we talk about looking for other forms of other kinds of life out there, you can. There are now several hundreds of exoplanets detected. But when you ask, can I detect any intelligence there? Radio is expected to be the way to answer that question. That if you can pick up a radio signal, and so both searching for complex molecules, which can be the building blocks of life, as well as the search for extraterrestrial intelligence, is one of the big drivers. And one of the things which is always there, that whenever you build something new, something which is 5 to 10 times more powerful than what you had, you will see a different view of the universe. New things, new objects which you never thought about or expected will pop up. And that is how science progresses, that when you put on a magnifying glass, you will see more details and much more than what you thought exists over there. And so serendipity will always be there in astronomy. So I will end over there, just leave this brief summary, but I'm happy to take questions if there are any. Thank you.